This video is going to focus on the specific situation where you're asked to interpret a confidence level. Let's say you flip a coin 30 times and you count 18 heads. We're going to create a 95% confidence interval for this problem. Here it is. We get the interval 0.425 to 0.775, and we write this interpretation of the interval. We are 95% confident that the true proportion of heads that will result from flipping a coin falls between 42.5% and 77.5%. Note, this is not what we write when we're asked to interpret the confidence level. Okay, this is what we write when we're asked to interpret the confidence interval. When we're asked to interpret the confidence level, we write something like, if we take many samples of the same size and create confidence intervals for each sample, we expect 95% of those intervals to contain the true proportion of heads that will result from flipping a coin. Another way we can write it, less common, approximately 95% of the confidence intervals created using this method will capture the true proportion of heads from flipping a coin. So what does that actually mean? So let's say we flip a coin another 30 times, and this is going to give us a different sample. Maybe this time we get 17 heads instead of 18. 18 gave us this interval up here. With 17 heads, we get this interval. It's changed a bit. We flip it another 30 times. This time we get 11 heads with this interval, then 15 heads, 13 heads, 21 heads, etc. Every time that we take a new sample, we get a different interval. And there's nothing special about any of these intervals. These numbers in any of these intervals are completely irrelevant. What we care about is the actual population proportion in between those two numbers. Now, since we're talking about flipping a coin, we know that 50% of the time we're going to get heads. And we can see 50% is in between these two numbers. It's in between these up here. All right. But sometimes, every once in a while, we're going to be extra lucky or extra unlucky, and we're going to get an interval that doesn't capture that true proportion. If we're making a 95% confidence interval, it's going to happen 5% of the time. So 95% of our intervals is going to have 50% inside our interval. And then the other 5% of the time, we're going to be too lucky when it comes to flipping this coin. We're going to get too many heads or not enough heads. And our interval is going to exclude that 50% and make us think that this is an unfair coin. Here's an actual graphic of it. So this is the mean of this distribution. It would be 50%. Right here we have 20 confidence intervals. In 20 confidence intervals, on average, 1 out of the 20 would miss. That dot in the middle there is the sample result, and then the lines coming off of that would be the margin of error. That green line down the middle is the actual population parameter. We want that green line to be within the interval boundaries. So that example that we just went through was for a p-hat problem, a proportion problem, which is what we use when we're dealing with categorical data. If we have a problem with quantitative data instead, we're going to be estimating the population mean, which means the way we write it is going to change slightly. So for example, if we took a sample of 50 students to estimate the average GPA of students at this high school with 90% confidence, we could interpret that interval by saying, we could interpret that confidence level by saying, if we take many samples of the same size and create an interval for each sample, we would expect 90% of the intervals to contain the true mean GPA of students at this high school. Or another way, a confidence interval created using this method will include the true mean GPA of all students in approximately 90% of all intervals created. So in other words, if we did this 100 times, 90 of our confidence intervals would have the actual GPA average in between those two boundaries, and the other 10% would be outside the boundaries. For two sample problems, just remember we're always talking about the difference between our two population parameters. For example, if we're making a 99% confidence interval to estimate the difference between the percentage of men and women who own pets, we could say we take many samples of the same size, we create intervals for each, we expect 99% of those intervals to contain the true difference in the proportion of all men and women who own pets. Okay, this is a key thing. And this also. We're always either talking about means or proportions, and with two samples, we're always talking about the difference. So if it was quantitative instead of categorical, we're just going to change it to, so here we're estimating the difference in the average number of pets, okay, or mean number of pets, And we could say about 99% of all confidence intervals created using this method will include the true difference in mean number of pets owned by men versus the mean owned by women.